Okay. Um, so the next homework assignment, the last homework assignment, we will shift from the date that's listed on there to that following Monday. I think that's December 10th. All right, and so we'll work with that. Um, it'll be on chapter 13. Probably be one more problem on chapter 14 that I'll assign at some point, but I probably won't collect that one. Okay. All right. So before we kind of jump into today, I want to show you a couple things. There's a variety of different types of equipment that are used for liquid extractions. Some of them are rather simple, some of them are more complex. It turns out that in a lot of cases for separation processes that use liquid extraction, the actual contactor for the liquid portion of this really represents a small fraction of the overall system. Because usually what happens is after you've carried out a liquid extraction, then you have to do further separations to recover the solute from your solvent and so on. And that equipment, is going to involve distillation, stripping, etc., and so on, depending upon what you're doing. So as a result of that, oftentimes that's at least as expensive and probably much more expensive in terms of the overall operation. But let me show you a couple pieces of equipment. Like, here's an example showing a system in which we have, starting over here, we have a piece of equipment that's our extractor. Let's see if I can get my pen working here. Yeah, we have our extractor. In this case, they're kind of showing it as a generic system, but it would probably, in this case, be some sort of a mixing type device. We'll look at some other different pieces of equipment here coming up just briefly. Some of these would have a stirring mechanism such that as you look down through this extractor, these would represent, in a sense, sort of like equilibrium stages going down through it. But then you see that we have to have post-processing equipment further downstream. I mean, we have some stripping operations, probably a distillation operation further downstream to do the full separations on it. Here's an example of a really simple extractor, maybe a single stage mixer settler. You simply mix the two fluids together, generate small droplet sizes, get good contact surface area between the two fluids, and then allow them to separate out. Go on over here. This would be one of these types of systems in which you would have, say, a mixing device going down through the column. There are other interesting devices. This is known as a car column. In this column, you can see it kind of oscillating up and down. What it essentially is you have what's something analogous to like a tray with holes in it. And they are literally moved up and down. And that motion generates droplets within one fluid phase within the other to generate surface area. There are other columns that are sort of like this, except that these plates with holes in them are fixed, and what they do is they pulse the fluid. So by pulsing the fluid up and down through those holes, you also then generate droplets and so on to generate surface area. So there's really a large variety of these kinds of pieces of equipment, and you can find all kinds. All right, so with that kind of background, let's jump back into chapter 13. When we left off, we were working on some examples here. And I think we quit here. We were working on an extraction. Let me just jump back a page here. We're working on an extraction of acetone from water, and we were using chloroform to do that. Okay, and in this case, again, just a reminder of some of our terminology. What is the raffinate stream? Without looking. All right, we gotta keep these terms straight. Okay, the raffinate stream. It's what?
The less liquid phase that doesn't have a solid coming out, like you extract it from
Okay, so it's what we call, yeah, so it's the stream that has the high concentration of what we call the diluent. In other words, we have a solute that we want to move from one phase to another phase, right? It comes in high concentration in this diluent, and it gets transferred over into the solvent, as we call it. So the raffinate is a stream that has a high concentration of the diluent in it. The extract stream, it has a high concentration of the solvent. Okay, so we're essentially moving it from, we're moving the solute from the diluent stream to the solvent stream. That's what we want to do. That's our terminology, right? They're all liquids in this case, but that's our terminology that we're going to use. Okay. So in this problem, we were given some volumes. We're carrying out a separation. We were given some densities. We ended up estimating the density of the acetone water mixture, and that enabled us then to figure out the masses of the feed and the mass of the chloroform that we're using as our solvent. Okay, so let's continue on with the problem here and finish this out. What we're going to do is we're going to assume that the chloroform and the water are immiscible. Okay? So no solubility between the two. If we do that, then we can draw a flow diagram for this particular problem. All right, so we've got coming in here our feed stream, which consists of acetone and water, and then we've got a chloroform stream coming in. We feed those into our extractor. In this case, we're considering a really simple extractor. So let's say that we mix them up, and then we allow them to settle. During that process, mass transfer is occurring. Acetone is moving from the water phase into the chloroform phase. It will reach some sort of an equilibrium state. And so coming out of our extractor, which includes, let's say, a mixing step and a settling step in a really simple case, then we're going to separate out the two streams. So we've got one fluid, which is water with some acetone in it. We've got a second fluid, which is chloroform with some acetone in it. Okay. All right. So how do we treat this? Well, one of the key aspects to doing any of these kinds of liquid-liquid extraction type problems is we have to know something about how the solute partitions between the two fluids under equilibrium conditions. And a lot of times that's the tricky part. So that's where you'll have to go to a lab sometimes and collect data if it's not readily available, or you go searching for data and try to find it. We're going to use something that we're going to call a distribution coefficient or a partition coefficient. Okay, goes by either term here. In this case, it's going to be specific for this system. So it's going to tell us how the acetone partitions between water and chloroform. The way it's defined effectively is it's going to be essentially the fraction, let's say, of the solute in the extract, right, divided by the fraction of the solute in the raffinate, as we'll call it, or whatever it was in the diluent initially. In this case, for this particular system, we find that we have a distribution coefficient of 1.72. Right? And so that's essentially the ratio of 2 mole or weight fractions representing concentrations. Our Y sub A, again, is going to be the concentration of the solute, in this case acetone, in the extract. right? So that's our solvent stream. And that's going to be divided by that mole fraction or weight fraction of acetone in the raffinate, which is a stream that contains the diluent or water, right? So we can use that information then to figure out the rest of the problem. Now, looking at this, based on our flow chart, what we need to determine in this simple liquid-liquid extraction example is we need to determine the masses of the acetone and the water in our raffinate stream. And we need to determine the masses of the acetone and the chloroform in the extract stream. So essentially right now, as it stands, before we do any more manipulations with this, is we end up at this point having essentially what? 4 unknowns, which means we need 4 relationships to get us there. Okay. All right. Let's think about the relationships then that we need. How many components do we have in this system? 3. So right off the bat, what are some of the things that we could probably do? We've been doing this for a variety of problems. We always do what? We do mass balances of some form, right? Okay. So with these components, then we could do at least 3 mass balances. And then we're going to need a 4th relationship. Where's the 4th relationship come from? Yeah, it comes from the equilibrium condition with the partition coefficient. So let's go do all those for the problem. So essentially we end up with, let's say, 3 mass balances. We could do one on the chloroform. And that's pretty simple, right? Because if we go back and we look at our flow chart, the chloroform and the water are immiscible, so all the chloroform has to come out in the extract phase, right? Okay, so that's pretty simple, pretty straightforward. So for the chloroform mass, it tells us that we were calling that M4 is essentially what goes in is what comes out, and what was going in was 596 grams. Okay. Water is pretty simple in this case as well, right? Because it's immiscible with the chloroform, which means it's all going to come out in the raffinate. We know what goes in this case. And how do we know what goes in? Well, in our problem, I think we can stay here. In our problem, we've got 195 grams of feed coming in, and 90% of that's water, right? So pretty straightforward. That all has to come out in this stream up here, which would be our M2. So let's do that. So we can say then that M2 is equal to 0.9 times 195 grams, which equals 175.5 grams. If we do then our last component, which is the acetone, we know how much acetone goes in because it's all going in with the water stream. It's distributed then between the water and the chloroform coming out. So we have to write that M1 plus M3 is equal to 10% of our feed, which is 195 grams, and so that's 19.5 grams. All right, so we've solved already for 2 of our 4 unknowns. We have 2 more to solve for. We have 1 relationship now, and let's use then our equilibrium relationship. So we know that K sub D for our acetone is equal to Y sub A over X sub A, which is equal to 1.72. But now we need to express that in terms of masses. So Y sub A, that's the fraction of acetone that's in the chloroform extract coming out, right? So we would write that as what? This would be M3 divided by M3 plus M4. And then the X value is going to be the fraction that's in the raffinate with the water in this case, so it's going to be M1 divided by M1 plus M2. Okay. So at this point now we have two equations, two unknowns. Pretty straightforward to solve for this. Solve for M1 and M3. And if you do this, you get M1 is about 2.7 grams. And of course, this would be acetone. And M3, whoops. M3 in this case is equal to 16.8 grams, let's say acetone. And this is, of course, in the chloroform phase, okay? And that's pretty much what we wanted to find. To kind of wrap up the problem, we can figure out the percentage of acetone transferred. And so the amount transferred would be what goes into the chloroform phase, right? M3. So this would be then 16.8 grams divided by what comes in, which was our 19.5 grams, times 100%, and essentially 86% of the acetone gets transferred in this case. All right, so that's a simple system, simple liquid extraction problem. We're going to make things a lot more complicated as we go along. We're going to think about stages. We're going to think about other aspects, whether we have dilute systems, non-dilute systems, we have multi-component systems or not. So any questions about that simple problem? All right, so let's move on. It turns out that a lot of systems aren't quite so simple. The liquids that we're using maybe as our diluent and as our solvent may be miscible with each other or have some partial miscibility, as it's called. So to keep it at least initially somewhat simple, let's consider again three-component system. Now we have to look at equilibrium relationships for three-component systems. We're going to take a look at a specific one here. We'll look at one that involves three components, and the components here are going to be water, acetone, and MIBK. To represent this, since we have three components, what's oftentimes done is to use some sort of a triangular phase diagram. And there's two different methods for doing that. One uses equilateral triangles. Another one uses right triangles. So we need to understand how both of them work. Let's start with the equilateral triangle to begin with. In this system, essentially each corner or apex represents a pure component. In the equilateral system, then, you can read off concentrations of whatever component you want by moving along a perpendicular line to the opposite side. So looking across this way, let me see if I can get my pen working here, across down along through here, we're essentially reading off water composition and amounts, right? Same way here for the MIBK, same way going down vertically for the acetone. Right? Now, there's a couple different regions shown on this phase diagram. You'll look up here, you see indicated here a so-called region A. Region A is a single phase region. Region B, down inside this envelope, is a two-phase region. Within the two-phase regions, you see that there are solid lines going across. Those are tie lines. So they would indicate how a mixture that would fall within that two-phase envelope would phase separate. So if you happen to be located, say, at something like this point M, point M is located by considering the overall composition of your system. Okay? That's locating the amount of acetone, the amount of water, and the amount of MIBK. Locate all of those, and you locate a point on there. That's the overall composition. But because it's within a two-phase region, what happens is that you get phase separation. So you don't have a system that sits right at that point. You have one phase, which you go to the other side of the tie line, has a certain composition. And you have another phase over here, which has another composition. That's where your system is going to be. All right. Some of you I know are pretty familiar with tie lines and phase diagrams, but I'm not sure everybody is. And so I just want to know, particularly Dalton, I know you haven't had material science with me, and everybody else has. And so in that class, that course, we talk a lot about phase diagrams. So I know that everybody else, including Zach, understands tie lines and so on. Have you worked with tie lines before? And using lever rule and knowing that, so you're comfortable with those? Okay, good. All right. So those kinds of things apply here, just the same way. You can use the same lever rule and so on with it. Okay. So the equilateral triangle is one way of representing this. It's not the only way. It's somewhat convenient in the sense that you can read off all three components directly. Not as easy to make. It's easier to maybe make the right triangle ones. So let's take a look at the same system on a right triangle diagram here. On this one, we have essentially two components listed. Really, when you get down to it. You have acetone on the vertical axis here, right? And you have MIBK on the horizontal axis. These are representing, in this case, again, fractions within the system, say weight fractions. In order to use it, we have to know that our third component here is the water. And so whenever you locate yourself on here and you read something off, you have to figure out what the water composition is. You can't read it directly, in a sense. Everybody with me on that? Okay. Again, tie lines are represented on there, right? So we know how they're going to phase separate in that two-phase region. All right. I'm going to do any more with that? Let's move on and use it in an example then. Okay. All right. So let's consider extraction of acetone from water, and this time we're going to use MIBK. So we're going to take 1,000 kilograms, 30 weight % solution of acetone in water. We're going to feed in some MIBK. We're going to mix it. We're going to transfer that over into a settler. And then we're going to look at the two phases which come out of the settler. One phase is going to be rich in MIBK. Okay. And second phase is going to be rich in the water. And the acetone is then going to partition between those two streams. All right, so we want to address how much MIBK must be fed to the process to reduce the acetone concentration in the water-rich phase to 5 weight percent. We're going to assume that the fluids remain in the settler long enough for equilibrium to be achieved. All right. Which of these two streams is the extract and which one's the raffinate? Coming out of the settler. Upper is the extract, right? And this is going to be the raffinate stream. All right, so how are we going to solve this problem? We're going to assume that we have equilibrium coming out of the settler, right? We're also assuming that we can get some sort of phase separation here, right? Which means that we're going to end up in that two-phase region on our phase diagram. Which means then that this extract phase and the raffinate phase are related how on the phase diagram? If we go back to this previous phase diagram, because we're going to use it to solve this problem, how are they going to be related? I don't want numbers. I just want to know conceptually how are they going to be related.
We'll find the 5% acetone composition. Look at that plan and use the timer to figure out.
So you just said it. So they're related via a tie line, right? They're connected via a tie line because they are at equilibrium. So if we can locate one of those two phases on this diagram, then we can use the tie line to figure out what the state of the second phase is. All right. So let's think about doing this. So we already know what's going on in the raffinate, right? We know the composition is 5% acetone. And we know that it's within the two-phase region. So all we need to do, that's going to fix a location for us, right? Say using, if we use the equilateral one here, right? We know that we are at 5% acetone. We also know that we are at an equilibrium situation where we have two phases in equilibrium, which means we have to be on this two-phase envelope someplace. So we can come over here to essentially where the 5 weight percent is. And then we can read off what the composition of that particular stream is. We know it's 5% acetone, but there's also going to be some MIBK in it, and there's also going to be some water in it as well. Right? Looking at this, looks like the amount of water is going to be in the 93% range. Look at the water. Here's the water composition going along this way. There's 90, there's 95. We're kind of right, maybe just beyond, just past halfway between them. So we're about 90, 93 weight percent. Which means that the remainder then of this has to be what? 5% acetone, 93% water. Yeah, so you got about 2% MIBK in it, right? So we know that that has to be the case. Since that's the case, then we can use a tie line. We're very, very close to this tie line which is shown on here, right? So we ought to be able to come up to this other side over here and effectively then read off the composition of the, which stream? The extract. Okay. Doing that, looking at them pretty carefully, we're beyond 85. I'd probably be a little bit less than where I drew that dot if I was careful. Probably going to be 86, 87%. if you're careful when you draw that in. Because we're just a little bit below the tie line, which is actually shown there. Okay. The amount of acetone that we have there is pretty close to 10%. All right, so the remainder would be water then for us. All right, so let's take that information then and finish out the problem. Okay, so at this point then we can say that in this phase, this was 5% acetone. We'll say 93% water, and let's say 2% MIBK. In the extract phase up here, we're essentially at about 10% acetone, about 87% MIBK, and maybe the remainder then would be 3% water. So basically use phase diagram and tie line. Okay, so now that we've figured out what the compositions are, we can then go ahead and address the question. It says here, how much MIBK must be fed to the process to reduce the acetone concentration to this? Okay. Let's go ahead and finish off that part of the problem. I'm going to go to the next slide, so I need some space here. Let's think about doing some mass balances. So what do we have? We have, we can think about an overall mass balance. And this would say something like MS, we'll say, is our solvent. We were feeding, in this case, 1,000 kilograms. And then that has to be equal then to the masses of the extract and the raffinate. So M sub E plus M sub R. Let's do a solute mass balance, or acetone mass balance. Coming in, we had 30% of our feed. And then we know that the extract has 10% acetone in it, and the raffinate has 5%. Okay, so far we've got two equations, we have three unknowns, right? Let's do a water mass balance. Coming in our feed, it was 70%. Going out, there's water in both the extract and the raffinate phases, right? So in the extract phase, we had 0.03 mass fraction, and then in the raffinate phase, we had 0.93 mass fraction in the raffinate phase. So now we've got three equations, three unknowns. We can simply solve, and we get the mass of the extract phase is something like 2,667 kilograms. The mass of the raffinate phase is 667 kilograms, and the mass of the solvent, which is our MIBK, coming in is 2,334 kilograms MIBK. All right. So questions about this? I mean, again, highly dependent upon us reading phase diagrams appropriately and being able to do that. Okay. All right. Let's take a look then at other types of systems. Now, we looked at one type of phase diagram that we could see. We had a single phase region and then we had a two-phase region effectively on it. But there are other possibilities, even with just three components. Shown here is another case where you see some miscibility between various pairs. There's miscibility between B and C and A and C. What this ends up giving us with these partial miscibilities is that there's essentially two areas within our phase diagram where we have a single phase region. And then we have another region where we have a two-phase system occurring. Okay? So again, this has to be data that's collected for whatever system that you're trying to work with. And some of that's out there. You can find this for various systems. You do some searching through the literature for things. Okay. All right. So if we think about an overall extraction process, we carry out a liquid-liquid extraction, some sort of an extraction unit, and then ultimately we have to do some downstream post-processing. That's going to be solvent recovery and so on. And you may even do further processing on the treated liquid up here as well. So it depends upon the system. All right. So let's continue on then, and I need to take a look at next portion. What we're going to do next is now we're going to consider cases in which we're going to do multiple stages of liquid-liquid extraction. Okay? Just like we did essentially with distillation, with stripping, with absorption, and so on. We're going to start with a fairly simple case. In a fairly simple case, we make some assumptions, right? So not all these assumptions are going to be valid in all cases, but we'll start with this one to get some of the general ideas. We're going to start with, and we're going to assume that we have a dilute system. And for us, that means ultimately that we're going to operate the extraction process isothermally, isobarically, and we're going to neglect any heat of mixing. Okay, so that's dilute. We're going to further make an assumption that it's very dilute. So we're going from dilute to very dilute. All right. If it is very dilute, that means that there's not much of the solute which is transferring between streams as it's going through the system. In fact, that's small enough that what we're going to be able to do is we're going to be able to essentially say that the raffinate and the extract streams are constant through our extractor. Okay? I mean, we did something similar to this previously when we did absorbers and so on, right, for parts of our system. And then, to simplify it even a little bit further for us, we're going to say that the diluent and the solvent are immiscible, at least as a first pass here. Okay. So if we do that, then we can do a quick analysis on this system. So what's shown here is part of an extractor with multiple stages. It's operating in a countercurrent configuration. Right, so our two liquid streams are flowing opposite to each other. They're immiscible all the way through. And we can go ahead and do essentially a mass balance on this. Right, so let's consider a very dilute system. So for this very dilute system, let's do then an overall mass balance. Okay, so the simplest thing to do is to take the control volume shown in the dashed region of our extractor up here. if we do that for this overall mass balance, right, we've got extract and raffinate streams going countercurrent to each other through the system. So essentially what we're going to have then is the following. If I look at, let's say in this case, let's say what's going in versus what's going out, we know that they have to be equal to each other under steady state. So in terms of what's going in our control volume that's shown, I would have an extract phase going in with a composition y sub j plus 1, because I'm at the jth. So that's over here. We also have going into this a raffinate stream, right? So this would be plus r times x naught. And that has to equal what goes out. Well, that's going to be extract stream times y1, it's coming out over here, plus a raffinate stream r with composition x sub j. And then we can go ahead and we can solve this for yj plus 1. Yj plus 1 then is equal to r over e times x sub j plus y1 minus r over e times x naught. That becomes now our operating line, right? And in this case, since we've assumed it's to be a very dilute system, R and E are constant, so it's going to have a constant slope, right? So this is a straight line. For a dilute system, we expect the distribution ratio to be a constant. So we can use K sub D equal to YA over XA. And this would be a constant. So it's also going to be a straight line for us. And so now with an operating line and with an equilibrium line, guess what? We are back to McCabe-Thiele. All right? So now we can use McCabe-Thiele to determine number of stages. And in fact, we'll do that. We'll do that as an example next time. And then we'll also consider if we're going to have a straight operating line and a straight equilibrium line, what else can we use? Back from strippers and absorbers, we had the Kremser method. So we can also use it as well. And we'll take a look at those next time. All right? So we'll stop here. Don't forget the homework for Friday. Have a good rest of today.